So let's start this session today. I warmly welcome you to our online training, especially for you students. I am very glad that I am the presenter today. And I strongly believe that you will learn today a lot of the structure analysis software, RFEM. So to me, my name is Daniel. I am the COO of Dlubal Software and mainly responsible for the whole operative business here at our company. Next to that, I am also responsible for our sales and marketing department. I am from a civil engineering background. I finished my master's degree last year and now I work here at Dlubal Software. Today, also my colleague Ismail is with me and he will guide you through the whole presentation via the chat. Ismail, can you introduce yourself, please?
Hello, everyone. Welcome to this webinar. We're very happy to have you today. I'm Ismail. I'm responsible for marketing, digital marketing for Dlubal since, how long has it been, Daniel? I think more than a year. And
Exactly.
yeah, today I'm going to be answering your questions. I will gladly answer all of your questions, so do not hesitate to ask any. And if I don't have the answer for any of those, I will ask Daniel to answer them for you. So yeah, welcome.
Perfect. Yeah, as Ismail said, he will be the second voice with me today, and you can ask him everything. We try to answer your question as good as possible. The training is interactive, so we will also allows you to model next to our real life presentation, more to that now in this presentation. Okay, I will stop sharing my webcam that you have the possibility to see more of the screen. So first part of this online training series, RFEM 6 for students. We have the part of the member design today. So we will give you an introduction to the member design and a few words to our platform, GoToWebinar. So you use, I guess, the web version. So you see it here a little bit like that. So you can show or hide your control panel. You can adjust your audio settings. So for the case, if you can hear us, just set up your microphone and your loudspeaker, and then you should hear us. And if you have any questions, don't hesitate to enter the question for Ismail. He will answer it to you. And after each chapter, we also get into a question, or I will ask Ismail if there are any interesting questions where we can show you something in the program. So the training series consists of 6 parts. We start today with the introduction to member design, and the next weeks, the next, I guess, 5, 6, 7 weeks, we will also have an introduction to the strength of materials with the program R section. Then later on, we continue with the finite element method or finite element analysis, also with RFEM 6. And the last 3 are some material specific designed training series about steel, concrete, and timber design. All things are quite easy, so they will give you an introduction to the basic concept and the basic usage of RFEM 6. And with that knowledge, you can refer to your task, exercises, and also exams of your study. So we do today some basic examples, some easy examples, which I had in former times also during my studies. And with RFEM 6, you can calculate and you can perform these structure analysis with our program and refer to your hand calculations. The biggest advantage of RFEM is that you need only one program. So in order to calculate trusses, single beams, continuous beams, or perform any steel or timber designs, you only need one program, and this is RFEM 6. No other external applications or other tools are required for that or for these examples. So what do we do today is, first of all, I give you an introduction to the 3D FEA program RFEM 6. So I will show you where you find all necessary tools, functions, options, and so on. Then together, we will do an introductory example and very easy single span beam with a single load. And then we continue with more analysis examples. So continuous beam, frame, truss, and so on. Then I will give you a short overview about calculation methods, first theory order and second theory analysis order. And then finally, also a short introduction to the stability analysis. Okay, so this will be our first example. It is a single beam with a single load here, quite easy example, and we will do here these steps. So I have attached the whole PowerPoint presentation also in the GoToWebinar control panel. You can download it. After the session, you will also get the recording of the whole training, a certificate for participation, and also all models we have done in this training session. We will send it to you after the session. Okay, perfect. So I will open RFEM 6. And before we jump right into it, it would be interesting for us if you work with two windows, with two monitors or screens. So we have prepared a few polls, and now it would be good if you could answer these polls. Okay, perfect. Then most of you have chosen. Okay. It's interesting. It's absolutely 50% using second monitor and the other one are just watching. So it's perfect for both of us, because those who would like to model with me, you are very welcome to do that. And the other ones you can watch, make some marks, and after the training you will also get the recording. So every time to watch some things again. Okay, the next thing, I have also another poll, because it would be also interesting for us. How is your knowledge regarding the whole structural analysis? So in which semester are you? Okay, perfect. I will show you the results. Okay, this is interesting because we did this training also yesterday with the Germans one, and there were a lot of, from the first semesters, from the bachelor, and now we have a lot of master students. Perfect. You will also learn a lot of things about RFEM as master student. Some nice things you can also use for your study. So, perfect. So this training will be kind of interactive. We'll prepare for each chapter different polls or different questions, just in order to recap the things we did in this chapter of this training. So this is a kind of interactive training. So before we jump right into the modeling, I will explain you the user interface of RFEM 6. So when you see RFEM 6 for the first time, it is useful to divide it in several, I would say to that areas. I will begin here with the menu bar. Here in the menu bar, you find the most important, or in general, all kind of commands, functions, and options. Just the file possibility here is that you can create a new model, you can save it, you can print it to graphics, import and export different models from other third-party software like AutoCAD or IFC models. You can export also these things. And then let's go to edit. Here you can edit or adjust existing objects, base objects, special objects. Then also view, insert, so you can create new objects like materials or sections, thicknesses, and so on. You can calculate, see the results, and then we have also here different tools and so on. Options is quite interesting. I work with a white window, so maybe some of you use a black window, no problem. When I go here to the display properties, I have the possibility to change the background, load dark background. When I click on that, it changes to dark, and I use here the dark background. So it's up to you how you will use it. I prefer the white background. So I go back here to options, go here to display properties, and choose here the white background and click on OK. We have today a lot of international students. So for those it's interesting that we also offer the language, the program language in different languages. So let's click here on program options and settings. And here in the tab of settings, you have the possibility to choose a program language, a pairing of those here. So for the French, Spanish, Italian, and so on, guys, we have here this language. Okay. Yeah, and then I have here also some other options, but for now it's enough to know that here in the menu bar you find all necessary functions and commands and so on. Good. Then we have here the symbol bar. The symbol bar is on fast access to the most important symbols you need during your modeling, calculation, and load application of your structures. If you want to create a member or lines, just click on that, and then you can create it. And then you can create it. I love working with them. It makes the whole process very fast, and also some visibility options here and so on. Okay, now let's go to the left side. Here we find a navigator. It's a very important window here at RFEM. With a navigator, it separates or it divides the navigator into 4 different areas. The first one is the data navigator. The data navigator organizes all important objects regarding the modeling, the load applications, load cases, combinations, and also the design. So when I want to create any new material, just right click here. I can edit or create a new material. The same thing here for objects. When I open it, same here for objects, intersections, and so on. And yeah, it is possible for all things. Maybe you can see here a kind of philosophy of RFEM. It's important to know that. So we have here the basic objects. Basic objects are the most important objects you need for your structure. So you need here nodes, lines, members, and each of these things is connected to other objects. So for example, when I want to create a beam I need the object member, because the member consists of a cross-section, and the cross-section again of a material. So these are these connections in the whole philosophy of RFEM. And the member is connected to some nodes, and the nodes are again here as basic object. And then I have also here special objects, and to every important object like a node, I have also types for node. So I can assign a nodal support to a node. And this is this is basically the whole philosophy in RFEM 6. Okay, now let's go to the other navigator. We have here the display navigator. Here in the display navigator, you see different options of displaying the objects, the model, things, loads, results. So for instance, I have here the activation of the global deformations. So I don't want to see them. I deselect it and I don't see or I hide the deformation. The same thing for, let's say the numbering. I can activate the numbering and I see the numbers like here, the member numbers or the node numbers. Okay, the next navigator is the view navigator. Here I have the possibility to create user-defined views. Currently I see the structure from that view, and when I just want to see the results from the global y-axis or against the y-axis, I can click here and I see it like that. Okay, then I have also the possibility to set up some visibilities. I activate here, for example, members and choose here the member by section. I am interested in the IPE profiles and I see it here like that. Perfect. So let's jump to the last navigator. This is the result navigator. Here I have the possibility of showing different results. So in this case, the global deformation, when I'm interested in the internal forces, I activate the members, activate the internal forces, for example, normal forces, bending moment, shear forces, and of course also the support reactions. Yeah, so much to that. Then we have the tables, where in the tables you have also a whole overview about all objects. You can also create objects in the tables. You can edit them. You can change values. This is a huge advantage because it gives you a very structured, very good overview, which is very clear structured. I can also jump here to the HEB profile, for example, and adjust it here with another profile. I can enter here a different name and then it will affect all existing members with that. So it's a huge benefit to control it also via the tables, and it will be also very important when we have the interpretation of results. Okay, now the control of RFEM 6 is quite easy. It's familiar when you are familiar with other software applications like CAD programs, AutoCAD from Autodesk, then you will get familiar also with RFEM 6. So with the left mouse button, I can select different things. When I go from the left upper corner to the right to the right button, then I can select all objects which are included in the selection window. When I go from the other side, I select all things which are which are also in this window, but not as wholes. I can select them as whole object. So everything what is touched by inside within this selection window, it will be selected. Okay, so much to that. When I want to select more objects, so I click here on one object like this member and I press the Control key on my keyboard, and now I choose another. I add new objects to my selection by pressing the Control key. So in this case, I select here different members. And when I want to deselect some members, just press the Shift button and I deselect some objects from my selection. Okay. By right-clicking, I activate a kind of context menu. It shows me some interesting information, like the display model. I can change it to the wireframe model. Maybe I can deactivate the loads or the results. And on top of that, when I click with the right-clicking on one of these objects, I can also activate the context menu of this kind of objects and can also do some nice things like, yeah, divide member, for example. Okay, with the mouse wheel, I can zoom in, I can zoom out. And when I want to rotate my working area, just press the Control key on your keyboard, press the mouse wheel, and now you can rotate your working window. Very nice. Okay, you can also use this view cube. It's a new function, RFEM 6, makes it a lot of easier to change your views for your structures. Okay, good. Yeah, this was it regarding the introduction to the user interface of RFEM 6. RFEM 6 as one program is 3D FEA program for the calculation of members, trusses, but also for surfaces, shells, and also solids. With RFEM 6 as a main program, you can calculate and get the results of internal forces, of stresses, of support directions, of deformation. When you want to perform different material-based designs like steel design, timber design, and concrete design, you need the add-ons. The add-ons will be part of our later trainings in 3 or 4 weeks that we jump into the steel design, concrete design, and timber design. Okay, now let's start with a very simple example. So for those who would like to model with me, now follow my steps. So I create a new model by clicking here in the file and create a new model. And a new window opens, and here I insert the name, model name, Singer span beam. I refer it to a project name. You can leave it here at examples or adjust it to some folders you have created in the past. It's up to you. I will create it here. Okay, we will use the type of model 2D, so XZ, plane stress. So we will get stresses in the both main directions, so 2, and this is enough for our examples today. The other registers aren't interested for now. They will be more interesting for the later trainings. And yeah, because we are international students, maybe for those who are interested in different units and decimal places, I can recommend here by clicking the units. And for those who are maybe from America or something like that, you can also change here, for example, the lengths into yards or feet, inches, and so on. So it's up to you how you want to use the units. Because I'm from Germany, I refer to my metric system. Okay, then I click OK. And the new working plane opens as new field, and I will start with the creation of nodes. So I go here to the symbol. I go here to the symbol bar and click here on new node. So I will use this symbol bar quite often. I click here and I will select here the first node here in the middle with the coordinate 0, 0. I click on OK. And referring to these grid points, you can see it snaps to that and it makes the setting or the creation of these nodes quite easy. And the next coordinate will be with an x coordinate at 7.5 meter. Now you see, okay, I don't have here this coordinate at the grid point. No problem. I can also insert here the coordinate. So in this case, 7.5, and in Z direction, 0. I click on apply, and the new node was created. Okay, now this coordinate system, this global coordinate system in my, in this node is a little bit uncomfortable, so I will hide it. I go here to the display navigator, go here to the area general, go to the axis system, and I deselect the coordinate system in the 0 point. So now I see here these two nodes, and in order to create now the line, I go here to this line, click here on new line, and now I just connect these two nodes with their line. And by clicking double right click or escape, I cancel this function or this command. Okay, now we have here this line, and as I said before, in RFEM we have the philosophy that different objects are linked to other objects. So now double click on this line in order to see what I mean with that connection things or the linked things, is that I can assign a member to an existing line. So I activate here this member and a new window appears. So now in this window new member, I can create a new member with a member type and assign them also a section. So, and in the studies, especially in the first semesters, you calculate your structural systems with no stiffness but in reality you have stiffness. In order to consider also the pseudo stiffness in your first semester, in the first phases of your study, I refer to the member type definable stiffness. So we create a kind of fake or pseudo stiffness. I go here to the register definable stiffness and I create here a new stiffness. Click on that. And now I insert here very small values, because in reality we have higher values, but for this example it's enough to insert here kind of pseudo stiffness. Okay, I click here on OK, click again on OK, close the member window, and then you see, okay, here we have the member activated, and I click on OK, and the example is ready. So you see here this member as this kind of thing. Now we need support. I go here again to the symbol bar, click here on assign nodal support, and I choose here the hinged support, so I will activate all translational forces. Choose here this node, right click in order to close the function, and now I go here back again and choose here the support with the roller in the X direction in order to release the X forces, and now I have here a single beam. I can show me the supports a little bit bigger just by right-clicking on it. I can adjust the size of the graphic, and now I activate load. In RFEM, it's like that when you want to create loads, you have to assign them to load cases. And by every new model, one load case, in this case, the self-weight, is already done automatically in the background. So I jump here to the load case, go here to edit active load case. And when I want to recalculate or to compare my hand calculations with RFEM, it's necessary that you normally don't consider the self-weight, because it can cause that you don't get the same results like your hand calculation. So for this simple example, I deactivate the self-weight and I rename my load case name with test load. Oops, sorry, test load. I click on OK. And now I divide here this line, because in the middle of this member, I want to create a node, and on that node, I want to create a single load or point load. So right click on this members, and I divide it by distance. And now let's enter here the value of 4.5 meters. The other one is calculated automatically. And now important thing is create on member nodes without dividing the member. So activate here this option. Then we get a node which is part of the member and doesn't divide the member into two members. So I click on OK. And now you see what I mean. We have here one member and this one node, part of the whole member. And the member wasn't divided into two members. It's a huge advantage, because then I can take a closer look to that member as one member. So, and now I create my single load. I go here again to the symbol bar, click here on new load. And now I click here on assign to nodes. So here I select the node in the middle. I can draw a selection window, click on OK. Enter here a value of 10 kilonewton. I say OK. And we have here the node. So, and the next thing is calculating the structure. So I have two possibilities. I can show me the results of this specific load case, or I can calculate everything. In this case, I will show me the results of this load case. Then this question arises, and I say yes, because I want to see the results of this load case. In the background, RFEM calculates the results, and then we take a closer look to that thing. Okay, so first of all, we see the deformation. The deformation is, of course, a little bit nonsense, because we have 99,000 millimeters deformation, because we don't have any stiffness. Yeah, but in this case, only the internal forces are for me interesting. And when you have statical determined systems, then the stiffness of a structure doesn't have an influence on the internal forces. Only when you have statical indeterminate or systems, then it has an impact of that. Okay, so I go here to members, here in the results navigator, and I activate here the shear force. Okay, I see here the shear forces, kilonewton, and then the bending moment, my, 18 kilonewton meter. Okay, interesting. So now I activate the support directions. I see the support directions, also pretty interesting. And now you can make a kind of plausibility checks. So compare the support directions with the shear forces, for example. And yeah, they are the same. So this was the first example. Pretty simple, of course. For the next examples, I will use real cross sections because this makes, in my opinion, more sense. It was just an example when you are in the beginning of the semester, you have started your bachelor, and you calculate, for example, some structural systems. Normally, you don't have any kind of information about the stiffness, and here you have the possibility how to consider these kind of exercises. Okay. On top of that, I would like to show you also one thing more. When you want to measure the whole things, I can give them kind of dimensions. So here in the symbol bar again, I go here and click here on the linear dimension. I click here to these nodes and say, okay, the second plane, and I can put here the dimensions depending on my nodes here, for example. It helps you in order to makes it easier for you. And one thing more, at each member, I can also show me the, I would say the tensile direction. So I go here to the display navigator again, activate here the tree structure of the members. And in this case, I can show you the bottom fiber. Yeah, this is the correct word, so not tensile direction, but member bottom fiber. And you see here this dotted line, and this shows you, okay, in which direction it is, the tension would go for the bending moment, for example. And also the member orientation and the member axis. But more to that later on. Okay. Now, this was it. This was the first example. And I have also a question prepared for you. So let's do this. It's a multiple choice question, so more answers can be correct. Okay, good. I will close this and I will share the results. So it was a multiple selection, so several answers can be correct. And in this case, all shown answers are correct. So I can create objects with the help of the menu bar, tables, data navigator, and also the toolbar. Okay, so let's go forward with the next example. This example is also for those who want to do this with me, so parallel with me.
Daniel,
yes.
Before we move on to the next example, I just wanted you to highlight the difference. I got the question: what's the difference if the member were split into two? There's no difference in terms of structural behavior, right?
Exactly, absolutely correct. There's no difference between the structural behavior and the results, just in the kind of result interpretation, it makes it easier for you because you can choose here this one member, and when you would like to see the results also at one member, just right click on member and create a result diagram, and you see here it as one result diagram. For example, this makes it easier. Or when you want to adjust or edit several members, and when you have here several node point loads, then it's easier for the handling and for the usage. So there's no difference in the structural behavior and the results, just in the handling of how you define these nodes.
Exactly. Thank you.
Thank you too, Ismail. Okay, let's go forward with the next example. I have a two-field beam. So I will save this here. And go here to file and say, okay, save as new. So I will create now a new file or new model. Two-span beam. I click on Speichern. Speichern is the German word for save. And I delete everything. Yeah, just select everything. Yeah, select everything and then press delete button on your keyboard. And I create now I will create two members. So now we have another philosophy for the two-span beam. So I click here on the symbol bar, new member, and now I create a new cross section, a real cross section. So I go here to the tab section, and as you see from the last project, RFEM remembers the last sections you were using for your projects. In this case, I will create a new cross section. So I go here, click on this button, create a new cross section. And I open here the cross section library. And I am looking for standardized profile. So in this case, an HEB profile. So I scroll a little bit down and then I will find here this HEB profile. I refer to the Euro norm, so more to the Euro code. And here I find HEB 300. This is absolutely fine for me. When I know the profile, then I can also insert here the name of this profile, and this makes your searching for the profiles much faster. So just insert here HEB 300, and you jump here to the existing profiles based on our search function. And this makes this whole thing very fast. And now I choose here this Euronorm, double click on my HEB 300 or just pressing here. Okay. So, and the same thing we can also do with the material. I use for this profile yes, easy S235 material, so in steel with a yield strength of 23.5 kilonewton per square centimeter. I can also create here a new one, searching for it with the help of the searching function. So I can enter here S235, and now I can choose here the one I would like to have. But I don't do it because I have it already here in this case, so I cancel it. And I just need here this one. Okay, I click on OK. And now you see here for my member start, I have here this HEB profile. Here, this material, I click on OK. And now I create a beam with a length of 5 meters. So just go here to this grid point, 5 meters, and again 5 meters. So the total length is 10 meters, but in the middle I have here this node. So the next thing is that I want to have here no support directions. So I activate here this nodal support again. And now a very interesting function in RFEM is that we have here also this apply button. And I show you how it helps you to define different or assign different objects easier for your structure. So for the first node, I would like to use here this hinged support. So I choose here this hinged, this node, click on OK. And now I don't click on OK, but I click on apply. And this node will be created automatically. And the next thing is that I change here the nodal support, choose here roller in the X direction, and select both nodes with a selection window. Click on OK again. And now I click again on apply. And now you see, okay, how easy you can do this with this dialog. I click on OK. And now you see here the structure. Perfect. So what's next? Yeah, the next thing is that we consider now different load cases. Because when I refer to my PowerPoint, I will show you my PowerPoint. We have here this two-span beam, and yeah, the information about the profile and so on, and also here 3 different load cases. And I would like to combine them in order to determine, first of all, the results, like support forces, internal forces, and so on, but also the governing load combination or the leading load combination that causes the largest internal forces, because we will have here also 2 additional load cases, like the imposed loads. At first for the left side of the beam, and then of the right side of the beam. Okay, let's go back to RFEM 6. Let's do this. I go here to the data navigator because you can also access the load combinations or the load cases from the data navigator. Just click here on load with the right click, load cases and combinations. It will open here this new window. And now this is also pretty nice. I would like to combine different load cases to load combinations. And therefore I can refer to some standards. I refer to the standard of our Eurocode because I'm from Germany. This is familiar for me. You can also refer to other standards. We offer a lot of other standards, like for the American standards, Canadian standards, and so on. And also the classical European. Okay, and now I will also activate the combination wizard because this is a kind of tool which helps me to create these combinations of load cases automatically. And I don't have to do it manually. This is a huge advantage. So I go here to load cases. I rename here this load case with self-weight. I activate here the self-weight. And I create 2 new load cases. So the new load case is imposed load left. I choose the correct action category, in this case imposed loads category A, according to my European standard. And now I copy the load case and say right, because with that load case I apply the loads on the right field of this member. Okay, now let's go through the tabs. So actions, I think this is pretty clear. I have here this permanent category, so permanent loads, in this case the self-weight, and here we can see, okay, which load cases are affected by this. Then imposed loads, yeah, these two load cases, and I have here different action types. Oh, come on. Different action types, alternatively, differently, and simultaneously. When I choose simultaneously, this means that both load cases can be combined with each other. Alternatively would be they would exclude each other. So, and simultaneously would mean that load case 2 can be combined with load case 3. Alternatively, load case 2 with load case 3 can't be combined. Okay, so let's go to the design situations. According to the Eurocode, the European standards, we have different design situation types. The serviceability state isn't interested for me, so I choose them, I delete them. Just the ultimate limit state, I go here through the information, and here you see short information about the combination rules. So the permanent factors, partial factors, and also here some coefficient combination, the partial factors. Yeah, so it's interesting how the program combines the factors for the load cases. So now you can see here the action combination. Now let's jump to the load combination, and let's pick this one. So here you can see the partial factors, that is 1.35 with times the load case 1 plus the other partial factors, partial factor 1.5 times load case 2, and so on. And now here can you see also these leading load cases or leading action categories. Is pretty interesting just to know, okay, how the program consider these different load combinations. Load combination is nothing else than a combination of different load cases under the consideration of these partial factors and combination factors. Okay, I click on OK. Now let's apply the loads to the load cases. And this is the pretty nice thing. I go here to the load case self-weight. I go here to the new member load. And what is now really cool, that I can stay here in this dialog, in this window, and can apply and assign all loads, also all loads to my structure, and change the load cases in this dialog. And this is a huge advantage, and I like this very much. So I click here on load case 1, self-weight. The load magnitude is in this case 2.5 kilonewton per meter. Now I select the members, draw a selection windows because I want to select all members. I click on OK, and now apply and next. I click on apply and next. And now this is a perfect thing, is I can change the load case to change here the load magnitude to 5 and assign it to the other member, but stay in the same dialog. This is pretty nice. Makes a lot of fun for me. I click on OK, say again apply and next, and the same thing I do for the right load magnitude. So for the right load and field, click here the right field, click on OK, and then in this case it is enough when I click on OK. So let's make a kind of plausibility check, go through all load cases. I have here the self-weight, the imposed load left, then the right one, the ultimate limit state. So this will give me a overall result of all load cases. Oh, and here we see here with the partial factors. So and maybe someone of you knows already what I want to reach with that example, because I want to see which load combination is responsible for the highest field moment and for the highest support moment. And this can be done with this ultimate limit state. So for this, with this design situation. So now I would say, let's calculate it. In this case, I choose here, calculate all. And a new thing to RFEM 6 is that depending on the power of your local CPU, you can calculate several load cases and combinations parallel. So this makes the whole calculation much faster, depending on the number of your kernels in your processor. Okay, now let's do a kind of verification or validation interpretation. So first of all, I always check my results in the self-weight load case because this is clear. I go here and check the results. So first of all, the global deformation. I see the global deformation here. When I want to see it with some colors, no problem. Go here and go here to the chapter or area members, and with with diagram, and here deformation, section colored. So this is a deformation, sorry. So the area deformation, members, and section colored would look like that. You can see here on the right side kind of control panel where you can see these colors. Okay, the next thing is the verification of the vertical or the support forces, and I see here as sum, okay, the sum of loads in the Z direction is 36 kilonewton, and the same sum here in support forces, so there is no deviation, and this is good for me. Okay, the next thing is, let's go to the design situation. And as I said before, I want to see, envelope values. So let's go to the members, and now you see here different kind of distribution values of the shear forces and also the bending moment. And I can say, okay, please show me the maximum values. So in this case, the maximum field moment. And when I take a look to the minimum values, I see it here. So the maximum or the minimum is here, minus 37. So the support bending moment. Okay, this is the summary, and now it becomes interesting because I want to see the results by member. So I go here to the table, static analysis, results by member, and I go here to the internal forces, and now I want to take a deeper look to the maximum field moment and to the maximum support moment. So the most minimum and the most maximum value. So, and here I go to the extremes area, and here I see these two values, these two results. So I see here the maximum value of the bending moment my is here, and now I see also the corresponding loading, and this is in this case load combination 2, and for the minimum value it's load combination 3. Now let's take a deeper look how the load combination looks like. So load combination 2 was this one. Yeah, I think this is pretty clear. And load combination 3, here we have the support moment. Okay, this can be done with the design situations. Pretty interesting tool to know and function to know. So one thing more, I go through the self-weight. Now you don't have to do this with me, just pay attention because this will help you when you are working with RFEM 6 and during your studies. So when you work with table books where you can interpret some, I don't know, where you can get some results and just put in your dimensions there, then you get some results for the maximum bending moment or shear forces and so on. It's important to know that these kind of table books don't consider the shear stiffness, and RFEM considers the shear stiffness. What is the shear stiffness? Taking into account shear stiffness leads to an increase in deformation due to shear forces. In order to deactivate, you have to go to the cross section and then you can deactivate it. So remember here the support bending moment of minus 11.18 kilonewton-meter. I go here to the sections, in this case HB, double click on that. And now you can see here the deactivate shear stiffness. And the influence of the shear is dependent on the cross-section areas AY and AZ. When I deactivate, they have no value. And the shear stiffness isn't taken into the account. And this can be also considered for your hand calculations. Because when you calculate with your hand, with the help of some tables in your books, then it is kind of rigid. Then the books takes no shear stiffness into account. Yeah, but in reality, there is a little bit shear stiffness, especially when you have solid cross sections or timber cross sections. However, it is recommended to consider the shear stiffness for the deformation analysis. But just in order to show you the different results, so remember minus 11.18, I click on OK. I calculate this low case again. So when I deactivate the shear stiffness, the part of the shear deformation is neglected. Yeah, this is something you have to remember. And now you see also here, okay, we have here different result, and this would be definitely the result you would get when you will calculate with the help of tables. Okay, perfect. Then I would say, okay, let's go to another poll. What happens when you disable the shear stiffness? Okay, I close this, share the results, and yeah, the most of you have chosen the correct answer. So when I deactivate or disable the shear stiffness, the contribution of the shear deformation is neglected. That's right. Okay, Ismail, any questions so far?
Well, so far I only got one question. I've already answered it, and it's about whether you can save load cases and combinations so you can use them for different projects. I mean, my question would be, would you really need that kind of function, since your load cases will always depend on your structure, and if the structure is completely different, it wouldn't really make sense to use a combination from another project. So yeah, the combinations are are usually project dependent. So I don't think you actually can do that since you don't really need it. But you should know that RFEM has a very wide range of predefined load cases and combinations. So I don't think you would really need to, define some certain saved combinations for other projects.
Yes, yeah, you are completely right. It depends on the project you want to calculate and you want to analyze. What we can offer too is that you can create templates. Yeah, you can save here, for example, this continuous beam as template with that predefined load combinations. When you refer to this template, the defined load combinations will also appear. So just go here to File, Save as Template, and when you open this template, it opens the project with these definitions you made.
That's a good point. And they actually said, what if we're talking about codes of standards of different countries? I think you could probably show that we do have standards from a lot of we do have a lot of different standards predefined in RFEM. And in case you don't have the standard you need in RFEM, of course you can define those and save them as template, as Daniel just showed right now.
Exactly.
Right,
Exactly, you're completely right. So if you want to take a closer look to the standards we support, go to your project or to your model and just right-clicking base data, or also here in the symbol bar you find this option. Click here, and as Ismail mentioned, we support different standards. Just go here to the add-ons. You can activate for maybe for the steel design different standards. So I click here on OK, and then you see here that we support here different standards. Yeah, and also here the different national annexes. Okay. So let's continue. Now I will do an example by myself, so I will make it a little bit faster. So just watch and learn. I delete everything again. And now, oh no, sorry, I don't want to delete everything. Now I want to add, well, hinges. So this is one-time statistical indeterminate. So I want to add here an hinge in order to make it statically determined. So how to do that? I click here on this member. Then I change here for a better visibility. I change here the visibility mode in order to do here this wireframe mode. Then I click with the right click to members and divide the member by distance. And now I would like to divide this member at a percentage of 17%. Why 70%? In my German student book, it's called Schneider-Barthabeln. There's a hint that in order to make the support bending moment and the field bending moment equal, the perfect length of the hinge is from the middle of the support 17% of the length of one of these fields. So I click here on 70.16. This is given by my table book. The division point is calculated automatically. Then I click on OK. And a new member was created because I will need this member for the creation of hinges. How to do that? Double click on the right member I activate here the option of hinges. A new tab appears right here. And now I go here to new member and choose new member hinge. So, and now it's important to define the hinges correctly. So in this case, the coordinate system refers to the local member axis, and I want to release the rotational, so I activate here phi y in order to create a moment hinge, and there the moment will be 0. When I want to release kind of a translation or deformation, for example, a normal hinge or a shear hinge, then I have to activate here these translational hinges. So when it's for the first time a little bit difficult, no problem. You can also release here, for example, normal forces, shear forces, and also the bending moment. And what will happen here? I activate it and I release it, and the value of this hinge will be 0 in this time. So I click on OK. Now I have here the member hinge at member start. And in order to see, okay, where is my member start and where is my local axis, I can show it to you. Right click on this member, local axis, and the other thing is the member orientation, and now you see it. So from left to the right, I see that the direction goes from left to right. So this means that I have my beginning or my starting node on the left side and my end node on the right side. And the member orientation is also compatible with the local x-axis of my member, and there I can also see the local axis. So much to that. I deactivate this, and now I calculate this structure again. And now watch out, pay attention, and see what will change. So we have assigned here a hinge, and this hinge means that the moment is there 0, and it is 0. Additionally, we see that the field moment is here 7 kilonewton-meter, and the support bending moment has the same value. Interesting, huh? So with these kind of hinged beams, in Germany we say to them Gerberträger. It's called according to the founder of these systems. Hinged beams, we can make these beams quite economically and also statically determined. So the previous beam was had one degree of freedom free, so it when you calculate it with the force method, you need to find this undefined value, and with this hinge we make it statically determined, and this is a huge advantage. So yeah, let's continue with the pole. Okay, I will close the poll, and yeah, the most of you have chosen the right answer. So Gerber beam systems or hinge beam systems are statically determinate systems. because we make them statically determined by adding or giving them hinges. In this case, this hinge. Okay, so in your studies, you work also with variables and parameters, and I want to show you how you do this also in RFEM. So I want, when you have the exercise, that this this two-span beam has a length and a parameter as L, and this has a parameter, and this has a parameter, then you can do this also for RFEM 6. So I go here to structure. This is something you don't have to do with me right now. Just pay attention. I will show it to you. I have here this global parameters. I click here on global parameters, and now I give them a name, L for length. Then I press the tabulator button. The unit group is in this case length, and definition type is in this case value. So I insert here a value, but I can also give the whole thing a formula, but in this case a value. I insert here 5 meters and comment it with length, that I know for later that with L is length meter. So, and the same thing for this distance, this E, so this 17%, I give them the name E. And now I don't want to use here a unit group. I want to use here factor, because it refers to the existing length by giving them a kind of percentage. And I give here them 0.1716. And this is the factor. Okay, I click on OK. Now I have to assign these parameters to my structure by manipulating the coordinate system or the coordinates. So the first thing is that this node will remain at its position. The next one needs to be changed. So I activate, double click on this node. I want to manipulate or set the formula, give the x coordinate the parameter L. So I click here on this arrow, click here on edit formula, and insert here just my L parameter, and click on OK. Click again on OK. And the same thing here for this node. I activate here the formula, and in this case it's L plus the factor E times L again, 5.858. I click on OK. And last but not least, I do the same with the last one here, just pressing 2 times L. Click on OK. Click on OK again. And now I want to change the values, so pay attention to the structure. I insert here the value 4, let's do 3, and I say apply, apply. And now you see how the structure was changed through these parameters. Interesting. Okay, so much to the parameters. Okay. Next thing is just a structural system with various types of loads and also some supports. So I delete this again. Now I will create the nodes with the tables. I go here to the structure, go to the tab nodes. So the next 2 examples you don't have to do with me. I will do it a little bit faster, just giving you an overview about how you can do things in RFEM 6. So I create here a new node going through the inputs with a tabulator tab on my keyboard, and now I insert here the coordinates 0 and 0, press then the enter button, and the next coordinate is, let's take a close look, 5 and 2, press OK, and the next one is 8 and 2, press OK, and now you see here that I have here these nodes. Now I create a new member, the same thing, the section is HEB 300. I click on OK and I connect the nodes in order to create my system. Right click, and the next part is that I assign these nodes kind of nodal support. So I choose directly a node. RFEM 6 remembers the selection, and this is the reason why the selected node appears here in this dialog. I say to them fixed, okay, and the same let's do for this one. And in this case I create here a roller in X direction. Now let's take a closer look to the definition of the nodal supports. So, very important thing. When I want to have in my support translational deformations, then I have to release them. So when I activate here one of these rotations or movements, then this support activates forces because it prevents the structure from moving or rotating. So when I want to have here at this support vertical forces, I have to activate the UZ, because then it prevents the deformation in this direction, and therefore I will also get vertical forces. And the same also for the rotations. Okay, so much to that. I click on OK. And now I leave here this load case self weight, and now I assign or I apply some loads. Just yeah, various loads. It is no realistic example. I click here on new member load, and in order to have also some linear or some linear load distributions, I can say, okay, I want to have that trapezoidal load distribution. I will start at the beginning of my member with 10, leave it here as 0, and say, okay, at 80% it should stop. I assign it to that member, and this is now the nice thing that I can remain here in the same window. Okay, apply and next. And the next member load is another one on the second member. So I activate here 1 and 2, give them here 20%, and choose the second member. I click on OK, and then I click on OK again. And now you'll see here the applying of these member loads, pretty interesting. And the next thing is that I want to have here a nodal point load. So I go here to the symbol bar, new nodal load. And when I have inclined loads, nodal loads, then I can separate it into different components, or I can also specify a direction. In this case, we do 10 kilonewton for the normal Z direction. I choose here this node, click on OK. And now the interesting thing is that I can can see the image where the node will appear on the whole structure. I can see it here. And now I want to specify the direction. So I activate here this option, and new tab appears. And there I say, okay, around the local y-axis, the local y-axis, I say, okay, minus 60 degree. And now it looks like that. I say, okay. And I see the direction like here. And one thing more, I can also give some nodes, kind of, imposed nodal deformation. So here I find this in the symbol bar. I say, okay, new imposed deformation. And in the opposite of the global Z direction, I say, okay, minus 20 millimeters. I assign it to this node. I click on OK. I say OK again. Now I will calculate the structure. And for me, will be interesting the results regarding the deformation, because I set to that node predefined deformation to that direction. And now I will see if it's correct. Okay, well, internal forces, you can see the internal forces, shear forces, normal forces, and so on. But for me, it's more important the vertical deformation of this node. So I activate the global deformation, and now I want to see the UZ, so the vertical deformation. And therefore, I just want to see the lines, because then it's more clearly to see the results. And yes, it's correct. Although there is a support, we have deformation at the support of 20 millimeters in the opposite global Z direction. Okay, so much to that. Okay, next example, and then we make a short break. I will delete this again. And now let's do a jump to my PowerPoint presentation. So this was the Gerber beam or the hinge beam. Here also I have attached the definition of this E. It's from my student table book, Schneider Bautabellen. Maybe you have something similar in your country, I don't know. This was the last example. And now we do this two hinged frame with a tension rod in the middle. So it's a pretty interesting example you can also do with the force method during your study. We have here this two hinged frame, and now we give them an additional unknown parameter by adding here a tension rod here in the middle. And we have here 3 different load cases. And now that task would be, okay, determine the support forces and so on, and also the degree of structural uncertainty. So it's in the statically determined, the statical indeterminacy. Okay, so let's go to RFEM 6. And let's model this structure. I will use for the columns an HEB profile we had before. This is also an example you don't have to do with me, because I will do it a little bit faster. I will do this, so 5 meters high. Then I go here. Now I make the roof 5 meters to the X, and also 3 meters high. Now you can also copy, rotate, or mirror some existing objects. So I select the whole left part of the frame, right click, and I want to mirror it. I want to create a copy of that. Choose the point here in the button roof, in the roof, and then here YZ should be the plane. I click on OK, and you see here now the other thing, the other side. Okay, the next thing is that we give them here an additional rod. And now we have different member types. You can see here we have the member type beam, and this member type is for all, this member type transfers all internal forces to other beams. I can add to that beam additional hinges. Let's do it in that way, and then I will explain you other member types. So hinges, I say to them the phi y should be activated, so there we will have bending moment hinges. And for that kind, because it will get tension forces, I can choose a smaller profile. So I will create a new profile. I will choose it here, CHC. I hope it will find. Okay, and I choose here this one. Okay, it's a kind of hollow section, circular hollow section. Can be used for the applying of normal forces. Pretty nice. And I say okay. Now I draw this tension rod from the left side to the right side, and I change here maybe the display model in order to see the right profiles. And now I create here the nodal support, click on OK. And now I apply the loads. First of all, I see here my load cases. I have self-weight imposed load from the last example. I want to change it. So I go here to edit. I change here this one to snow, and this one to wind, and this one to temperature, because then you see all possible load applications we can do. So distributed loads, single loads, temperature loads, or nodal restraints, nodal deformation, and so on, and now also the temperature. Okay, next thing is that we activate here the base, deactivate here the standards because we don't need it this for now. I click on OK. Now I apply the loads. I jump here to the snow load, go here to the member loads, and I have here 1 kilonewton per meter. And now the load direction for snow loads is different. It's not on the true length, it's on the projected length. I choose here both members. I click on OK. I say apply and next. And now I choose here the low case wind. Here the direction is to the global x-axis. So I say true length, first of all on the column. So it doesn't matter if you have it on the projected length or the true length, because the column is vertical. Column, I say okay. And now I want to refer and apply my load according to the local member system. So I say, okay, I want to have it like that and put it here. because normally the print pressures are on the local axis of my inclined beams. So I say apply next. Now it looks like that. And now the temperature will do it here a little bit different. I cancel the whole definition because I wanted to show you how you can make an object selection. So first of all, I want to display different cross-section with a different color. So I jump here to the display navigator, scroll down to the area of the colors of rendered objected by, object property, member, and now I want to see them by the sections, like here. So I have here the, I would say brown color for this HEB profile and the green color for this circular hollow section. And now I want to select all sections with the type of HEB 300. In RFEM, we have here a nice function. Let's go to the data navigator and go here to the guide objects. And here we have the object selections. Right click, create a new object selection. And now I want to do an object selection with the power of members. And the definition is the section equals, and now I choose my reference member, and this is this one. And now you see, okay, equals member or cross section number 3. I say okay, and now, oops, and now I see here these cross section are selected by the help of this object selection. And now the nice thing is now I can apply the temperature very easily because these objects are selected, and I choose here the temperature change 35 and local Z, and I say okay. Good. Now let's calculate all load cases. Then we will take a closer look to the results. Okay, perfect. So as you can see here, maybe for the snow load, you see here the deformation. You see here the deformation. And also the internal forces, and as assumed, the tension rod get tension forces. And also when I take a close look to the members, I see it like here and so on. So now we have in RFEM different member types. This member type is a beam, but with hinges at the end of the member. In order to consider the same structural behavior, I can also choose the member type truss. Truss is nothing else than a beam type, but with hinges, with moment hinges at the end of the member. Then we have also another thing. This is truss, only normal forces. So only normal forces are activated, no bending is possible. When I have the truss, the member can take some self-weight, and truss only normal forces. Let's do this truss only normal forces, and you will see, okay, how it will affect the results. Yeah, and as I said before, this member type don't consider any bending moment, only normal forces. Yeah, and although we have here self-weight activated and the circular hollow section has some weight, the bending moment isn't considered here because we have the member type truss only for normal forces. Okay, so much to these member types. We will use this member type truss only normal forces for the next examples regarding the truss structures. But before we do that, we will make a short break and I will ask Ismail, is there anything, any questions we should show them to the publicity, or do you think we can start with the break?
You mean now, right?
Yes.
Yeah, no, we're good. We don't have any further questions. I just want to say that when you were talking about notice supports, I sent you guys in the chat a link to a useful video about notice supports that you can check out on our YouTube channel.
Okay, perfect. Okay, before we go to the break, I have prepared another poll. I will launch this and please answer this. Okay, good. I will close this poll, share you the results. And yes, you are right. The most of you are right. Beam members transfer all internal forces because they are rigid members, and when they are connected to each other, then all internal forces are transferred. Okay, so let's do the break. I would say 5 minutes, and yeah, see us in 5 minutes. Okay, Ismail, can we go ahead?
Sure, yeah, of course.
Okay, perfect. So I show you RFEM 6 again, and what I have forgot and would like to show you is the following thing. We have here the same frame. I double click on this truss and I choose here again beam with these two, with the two hinges at the end, and the member start and at the end member end. Now, come on. I click on OK. And what I would like to show you is, is when you want to have here an whole hinge to be considered. Then it's false that you assign to every member an hinge. So when I would assign to that a hinge at the member end, and to that a hinge to the member start, then this would be nonsense, because then RFEM crashes because we have a hinge chain, and this hinge chain is not right, yeah, because it would cause an instability in the program, and the program doesn't calculate this. So we can test it. I activate it. Yeah, and you see here this error and this failure because we have here a singular stiffness matrix, because the structure is unstable in that node because of the chain of hinges. And in order to avoid this, you have to remember just one thing. If you want to build here a complete hinge which all members connect, then you just then you have to leave at one member without a hinge. So I show you now the correct modeling of this thing. I deactivate here the hinge, and now I will to have here this whole triangular thing, that all things are connected with hinges. So first of all, I change here these nodal supports to fixed ones, and the next thing is that I assign here at the top also a hinge, and here the same thing for this member. Click on OK, and this would be the correct definition when I want to consider it as, I don't know the English word for that, but when I want to consider here everywhere hinges. Now I calculate this, and when we will take a closer look to the moments, to the bending moments, then we will see that the definition was correct. Yeah, and we see it here. Here we have the bending moment, and every time where is the hinge, we have 0 moment. And this would be the correct definition of the hinges for that case, for example. Okay, next example. In truss, what we have here. I go here to the PowerPoint. So ideal truss. So yeah, we have here a truss with yeah, with different members, and the members will be members with a member type truss, only normal forces. So an ideal truss is, yeah, weightless, straight, only carries normal forces or axial, tensile or compression forces, and all loads are applied on the, all loads are applied on the nodes or on the hinges. Yeah, this is an ideal truss. In reality, we don't have any ideal trusses, but in your study, you'll learn how to calculate these trusses. So, and now I show you how to consider it in RFEM. So I delete this structure again. I create here a new single member with the truss. This is important for the right consideration of this truss. And the section is, yeah, I take here again this HEB 300 profile, and I click on OK. And now I create here this new member, but this was unfortunately the wrong thing here. I have to do this here by the general option of thing, so I have to redone it, but no problem. And now I put here the length and also the direction. I have here 3 meter. All sides are similar, so I choose this one. 3 meter. Angle in work plane is here in this case 30 degrees, sorry, minus 30 degrees. Then I can do this like this one. I change this. I have here like this one. So, and now I draw or I can refer to this member. I say OK. From that array, and now I have here this triangle. And now, very important, my favorite function in RFEM 6, I select everything here. And now per drag and drop, I can copy selected objects very easily. So I press the Control key on my keyboard, click on the left corner node here, and per drag and drop, I copy it from there to there. Same thing again. I can copy things very easily. And this is my absolute favorite function. Please remember it, you will use it very often. So then I create again a new single member. I choose here the same object properties in graphics. So this enables me a smooth way to insert different objects or members, for example. I click here on OK and connect here these two members. So, and now I have to correct the member type because I saw I have created the member type beam. I select everything, and now it's okay when I just double click on one of the members, and you see, okay, member, there are several members to assign, and I choose here truss, and I can change all members at once to the member type truss, only normal forces. Perfect. So the next thing is assigning them here nodal supports. I give here them a nodal support, hinged, and here again. I make them a little bit bigger, so like that. And now I assign here to these nodes nodal loads. So I go here, new nodal load. I select the first nodes with 10 kilonewton, click on OK, say apply and next. And the next one with 20 kilonewton, I assign to the right node, click on OK, and say OK again. So again, that show me the results. I say yes. And the special things about the trusses is, and also about the member type truss, only normal forces, is that only the stiffness in the length direction is activated. Yeah. So let's take a closer look to the results. And you see no moment, only normal forces. And when you see here member type truss only N, then you see, okay, only normal forces are carried. And only the stiffness in the length direction is considered. So let's go back to the normal forces. Now remember, all compression forces are in general negative, and in RFEM, when you have the standard design options, blue, and all tension forces are in general red and positive. Yeah, and you see, okay, here I have the tension cord, and here the pressure cord, and here you see the different normal forces. So again, negative normal forces are pressure members, and positive normal forces are tension members. Okay, so much to that. And then there are also some members called null members, Nullstäbe in Germany, which don't carry any loads. And there are different rules how to determine these kind of null members. And you can also do this with RFEM. So I will add now these null members. I don't know if the English word is the correct one. I select here the properties, the same like here. Click on OK. And now I draw here this member. And now again with my favorite function, drag and drop, press the Control key and copy it from one side to the other one. And now the nice thing is you can also add more things to your selections, and I can easily drag and drop it like that. Perfect. And the last also for that. Okay, good. And yeah, there are different rules in order to determine these null members. These are the members which don't carry any normal forces, but are sometimes responsible and also mandatory for the whole statical indeterminacy. So let's take a closer look to that. I will calculate it again. And a classical student example would be, okay, calculate this truss structure and determine also the null members, so the members who don't get any normal forces, and then you have it. And also determine the positive and negative normal forces, so the tensile and pressure members. So as you can see here, okay, these things get some normal forces, This is a little bit strange, but I can tell you why that to get these normal forces, because I considered the self-weight. Here in this low case, I deactivated. Now I calculate it again, and now you will see that these members don't get any normal forces because they have this structural behavior. Yeah, and no normal forces. So much to that. Okay. So I have a poll prepared for you, which summarized this chapter a little bit. So this one. Okay. Let's close this poll. Yeah, and the correct answer is that compression members are usually truss members with negative normal forces. And in RFEM 6, this is usually the case for these blue colored normal forces, because there we have also a negative value, and now you know it. Okay. So this was an ideal truss, but in reality we have trusses which also carry some loads and are also where the load are applied on the structure, not on the nodes. So I delete this again. Now I will do an example where you don't have to do this with me. I do a kind of this example, a spanned beam. So here we have a normal beam which carries bending moments, which is also bending active, and this supporting tensile structure is just carrying normal forces. So let's model it. So I create here again a member with a HEB cross section. I click on OK. And the length of this member is 16.5 meters. I say OK. And now I divide this member internally into two nodes in order to get two nodes. So right click on that, members, and divide member now and intermediate nodes because they will have the same length. I click here on 2 and select here this option. This option will cause that the member is not divided into different members, but we will get the nodes. So here we have the blue nodes, and you see, okay, when I go through the member, it is one member and not three members. But I have here these nodes, and this is pretty nice because then I can refer to this structure more easily and see the results more easily. So the next thing is that we create another kind of member. In this case, the truss, only normal forces. Section is in this case this IPE 200 profile because it's a little bit smarter. And now I just choose here the length and direction, 1 meter, and go here 1 meter upwards. Here again And now I want to create here also a member. I choose here these two nodes and these two nodes by clicking on the Control key. Right click on one of the nodes. I say move and copy. Now I can create a copy of the selected nodes. I say yes, I want to activate it. I choose here the displacement vector at the Z, and this is 2.3 meters. I say okay. And now I will connect these two lines. So I take here this beam. In this case, the truss only N, and I refer to this cross section. So I choose here always this select object properties in graphic. I click on OK. Now I draw it. So perfect. So I change here the display model, and now I see okay that these local node coordinates are incorrect. So I want to change them. I double click on one of these nodes, and I can change here the coordinates, and in this case I want to change them at -1.4, so it goes a little bit upwards. I say okay, and now the structure looks like that. Okay, now I refer now I have to assign some nodal supports. I choose here these nodes, give them this fixed support, and the same here for this one. This will be a roller support in X direction. Okay, and now I create also an new member load. I go here, click on new member load, enter here a value of 15 kilonewton per meter, click on OK, and choose here this member. The high advantage of this division of intermediate nodes is that I can assign this load and apply this load to one member and don't have to click on these three members. This is one advantage when I divide the beam into into one beam. So I divide this beam into internal two nodes, but the beam will consist as one beam. This is a high advantage in RFEM. Also the loads I can show a little bit smarter. Yeah, and now I calculate the result. Say yes. And now you see here the result. You see here the tension forces. Yeah, because we have here activate the normal forces and also the bending moment. And this example is pretty nice because it shows the following thing. When I take a closer look to the deformation, you see, due to the load applying on the beam, it deformates it downwards. Yeah, but we have here these tension members which carries the member, so the beam, and this is also the reason why these things get tension forces. And this explains also this interesting bending moment distribution, because here we get additional normal forces. You can see it as an additional support, and this is the reason why the bending moment looks here so nice. Also the normal forces. Okay. So the
We
last
do have a
example.
question,
Yes.
Daniel, real quick about this example. I got a pretty interesting question talking about whether about how we would model a double beam if for some reason the bottom chord fails, and if it's already in place and an engineer for some reason decide to add another beam, how would you model that in RFEM? Like, would you add another beam over the old beam, or how would you try to model that in RFEM? I'm not sure I understand the question, but if you do understand, maybe you could answer it. Like, if you have already an old beam as the bottom chord, and you want to add another one in real life, how would you model that in RFEM? Because from what I can answer this question, I think like you can either edit the beam or like edit the section, or if you want to add another beam, logically speaking, you would need different nodes, because you can't just pretend that two beams are connected to the same point. So I mean, that's how I would answer it. But if you have a different answer, like, is it actually possible to add a so-called built-up after having the first beam already in place? Is that even possible?
Yeah. In general, everything is possible in the 3D FEA program. The question is how you consider it also regarding the calculation. And my approach would be creating the existing structure, of course, and then also assign the new member with some couplings. We can support here different couplings, or yeah, how it's called. Different coupling, hinge. So these couplings, rigid, hinge, and when I connect different beams with these couplings, then I can consider a structural behavior like that. But this is a really not so an easy or difficult task for a structural engineer who is more familiar with the consideration of these existing structures. In general, I would calculate it as structural engineer, first of all, with the existing structure, and then in a second step, neglecting the existing structure, considering only the new added structural elements. This would be my approach.
Thank you. Yeah, it is a very specific question, but the most important thing is that you do have the option of choosing this kind of couplings in RFEM, which is very important as a provider of solutions to these kind of problems. So depending on what you decide to do, how you would approach the problem, you will have the tools for it in RFEM in case you decide to go with the different couplings approach. So yeah, thank you.
Okay, let's go ahead. I have a possibility to generate trusses very easily. We have in RFEM the possibility due our Dlubal center and blocks that we can generate blocks for example, trusses very easily. So I click here on blocks, and a separate window will open. Sorry, I forgot to click this. Okay. Unfortunately, it doesn't work. I try it again the last time. Okay, this is the so-called presentation effect when I want to show you. Ah, now it's there. Okay, perfect. I was lucky. Okay. So here in the Dlubal Center, we have blocks, and there I can create trusses, for example. I choose here this 2D truss, and I can generate very easily by just giving this block any parameters, this kind of truss. I click on OK. I choose this one. I say yes, because now the block requires the model type 3D. I say yes, because this model type 3D we will also use for our next examples. So next thing is that we see here this truss, pretty nice. For those who are familiar with programming languages and like scripting, these kind of blocks were created with the programming language JavaScript. So if you are familiar with JavaScript, you can also program your own blocks, and this is very powerful when you can do this. And this is also one of my future theories regarding the whole civil and structural engineering field, that the students should know how to program, yeah, because then they have a real advantage modeling and defining and designing their structures with different parameters. So I can only recommend learning JavaScript or any other programming language, even if you are a structural engineer. So let's go back here to structure. I put here number of base 6. The input via I can choose here between 2 different lengths. I choose here this one. Total length is 12 meter. So the length of the outer base is 3 meters, or the inner base is also 3 meters, and the height of the truss is 2.5 meters. So, and now I choose some cross section which would also appear in the practical structural engineering field. So for the top chord, because there we get a lot of tension and compression forces, I would choose a more stiff profile. So I create a new cross section. It will be an AGA 300 profile, and the great thing is that I can create the profiles here in this dialog. Just go here 300, so AGA 300. And now I go here, AGA 300. And yeah, this is enough for me. Now I copy it and just rename it from 300 to 160. Same here. And then I copy the same thing here again. And now I will have here an IPE profile, also 160. This one. And I say, okay. Now I can assign the chords to my cross sections. So for this one, no, sorry. For this one, I have here this HEA 300. The button chord is the same profile. The diagonals have this HEA 160s, and the verticals, because they don't get so much forces, an APA 160. Okay, then I click on OK. And I see the structure here. Very nice, because I see all different cross-section according to the cross-section with a different color. This makes it more, it makes more easier to see suddenly the correct cross-section. Yeah, and you see, okay, the trusses are modeled as members with hinges. So what you can do is selecting all members, double click on that and give them here this truss behavior, and then you have the same effect. Okay, so much to that. Okay, last part of our online training is the calculation theory, second and first order analysis, and also then the stability design or stability analysis. So for that, I will model a very easy Euler case. So it's just a fixed cantilever column. So I create this one. I click on beam, and now the section will be an HEB profile. I click on OK. 10 meters high. (10 meters high), and now we need here a fixed support, and on the top we need here a single load. In this case, I give here 100 kilonewton as vertical load, and also a small horizontal load in order to see the effects of the analysis according to the second order. I click on OK. Now it will be interesting. Oh, sorry, this is not correct. That's one. I have to assign this one to the number 2. Now I go to the load cases, because in the load cases I can assign the static analysis. So first of all, I will change here these 2 load cases, and I say to that theory first order, and this one will be the second order. So, and here you can see static analysis settings. I have here a geometrical linear. So in general, load cases are calculated according to theory first order. So I have a geometrical linear calculation. When I want to consider P delta or the second order, I have to change here the static analysis setting. And normally load cases are calculated according the second order. So I activate it. I go here to load case 1. Okay. You see here the load case 2 and load case 1. And now I want to calculate both load cases, and then I will show you the differences in the calculation. I say calculate all. So, okay. Now I will create new windows. So I will create a new window here. And again, now I can show me several windows vertically. This one I don't need. So again, perfect. So this will take a little bit. Here the same. Okay, good. Here we have the results of the first order, and here we let show us the results of the second order. So first of all, the normal forces, but for this fixed column, cantilever column, the bending moment is for me more interesting. Okay, so let's take a brief look. I think calculating the bending moment of this cantilever column is no big problem, because 10 meters times 10, so 10 kilonewton times 10 meters, so the height, this is my bending moment here at the support. This is according the first order. So when I calculate according to the second order, to the first order analysis, then the program makes the equilibrium at the undeformed system. When I calculate according to the second order analysis, then the program makes the equilibrium at the undeformed system. So you see here the differences. Here, first order, 100 kilonewton meter, and here, 106 kilonewton meter. So we get more moments. And why? Yeah, because we have here also this vertical load, and this times the horizontal deformation on the top equals this bending moment at the bottom. So I can explain this here a little bit better. So I will show me here the deformation in the horizontal direction, and then here the bending moment. Okay, so let's check it. So 100 kilonewton times the deformation, the top deformation of 68.2 millimeters equals an additional moment of 6.82 kilonewton meter times plus the normal bending moment according to the first order analysis. So this 10 kilonewton times the 10 meter equals this 100 plus this 6.82. This is the additional effect according to the second order analysis. Okay, let me summarize it. So you have here 68.2 millimeters times the vertical load 100 is 6.82 kilonewton meter. Now plus to the bending moment according to the first order analysis of this 100 equals this 106.82 kilonewton meter. And this is the difference you have to know when you calculate structures according to first and second order. Okay. Now stability analysis. You see here we have the Euler case 1. We have 4 different Euler cases. This is something you have to know. And for the Euler cases, you can also calculate and consider the buckling lengths and also the critical loads. And in RFEM, we can also calculate and determine these things. I will leave here this example, but delete here the force in X direction. I say okay. And here the same. Okay. So, and what I do now is performing a stability analysis. And therefore I have to activate an additional add-on. I can go here to edit model base data, and I jump to the tab add-ons, and I activate here the structure stability. So what does this add-on do? It performs according the eigenvalue method buckling shapes or buckling forms, buckling lengths, and also critical load factors. So let's do this for this simple example, because everybody in your study has already calculated maybe a critical load for these Euler cases. Yeah, we can do this also we can do this also in RFEM. So let's go here to activate this load case, and the only thing you have to do, and this is almost nothing, just activate here the critical load with the structured stability add-on in the low case or also in the low combination. In this case, we make it easy. We will use the low case, and you can also edit it. So here, edit stability analysis settings. We have here different stability analysis types, eigenvalue method, linear, non-linear. For our reasons, it's enough when we use this linear possibility. And here we can set up how many eigenvalues we want to have. For this simple Euler case, yeah, 4 are enough. Normally it should be also 2. And I say why? I leave it as 4. And now let's calculate it. And now you will see, okay, we have the normal static analysis, yeah, this SA, and then that structure stability, yeah, ST. Okay, and now let's take a closer look to the results. We have here the summary, stability analysis, okay, and then also here on the left, stability analysis, also here in this, yeah, in this pull down menu. And this is pretty easy. So when you want to get the normal results like internal forces, deformation, you go to the static analysis. And when you do a stability analysis, just go here and see the results. So what can I see here? First of all, I activate here the control panel again. I will show me here this mode shapes in order to make the display factor a little bit bigger. So this is important to know. The first eigenform or the buckling shape, yeah, it's this one. And why it's this one? Because the buckling shape said to me how the structure would fail when I would increase here this vertical load. And this would be the failure form, yeah? And in this case, the profile would fail around his weak axis, yeah, because with the flanks shows to the X direction, and this is the stiffer direction. And so the first failure would be around his weak axis. And this would be the first eigenvalue, so the first eigenform. The second one would be around his strong axis. Yeah, this is interesting. Yeah, but this is clear. So when you would design this beam, then you would add here additional lateral supports by avoiding this failure around the weak axis. Okay, so let's go to the results in the tables. We have here the critical load factor. What is a critical load factor? The critical load factor specifies which factor can be used to increase the load until the structural system fails. So what does it mean? When I times the 100 kilonewton with a critical load factor of 4.4, then I have 400 kilonewton. And when I would calculate the structure again according the theory second order, then the program would not calculate it because it says it is unstable. So if the critical load factor is smaller than 1 according to the first theory first order, then the structure is unstable when I calculate it according to the theory second order. So to put it in a nutshell, the critical load factor says to me, okay, how much I have to multiply it with this factor until the structure fails. This is the critical load factor. The next thing, the magnification factor. This factor describes the relation between the moments according to the geometrical linear static, so theory first order, and the second order analysis. So when I would have here a result at the bending moment here at the bottom, and I would multiply this result by this one, I would get the result of this bending moment according to the second order analysis, so to the geometrical nonlinear analysis. Remember, second order analysis is a geometrical nonlinear calculation. So now let's make it unstable. I'm really looking forward to it. So we said, okay, 4.435. So let's go to the theory second order and let's increase here this load to 444 kilonewton, because then we are over this critical load factor. I click on OK. And I calculate it, say yes. And you see, okay, an arrow appears. Why? Because the stiffness matrix is singular, the structure is unstable. Because the critical load is, the existing load is critical than the capable critical load of this beam here. So, and when I want to take a closer look to the buckling lengths, I can go here by results by members, go here to effective lengths, critical loads, and here I see the effective length vector and also the effective length, and also here the critical load. So the eigenmode, the first eigenmode shows me an effective length of 20 meters. Yeah, so when I would perform a stability design in steel members, this would be the equivalent length when I would do it with an equivalent member method, and also here the effective length factor, and also the critical load. And this is pretty interesting because the critical load is the 100 kilonewton, so the existing load on the structure times the critical load factor. So, and yeah, 20 meters, this is also the case for this Euler case 1. When I would have an Euler case 2, then it would be 10 meters. Okay, and important note is that I have here deactivated the shear stiffness in order to get the same results like in my hand calculation, because we have here still deactivated the shear stiffness, but in reality you have a kind of shear activation of the profile. So this is also the reason why it's in general activated. Okay, so last example, I have a fixed frame where we also take a closer look to the different buckling modes, buckling shapes, because then it, I guess, will it be more clear. So what I will do is I copy the whole thing here. And now again, my favorite function, drag and drop 10 meters along the x-axis. I put here an additional girder. It is in beam. The section is an IPE 300. I click on OK. And now I connect here these two top nodes and change the height of the nodes to -6 meters in the Z direction. And now let's do the same as we had it for the Euler case 1. I go here again to the theory first order, and now I activate here 10 eigenvalues. So yeah, and I say, okay, calculate it please. So now let's take a closer look to the results of the stability analysis. So, and what we see here is pretty interesting. So because we consider the 3D model type, we see that the first eigenvalue is a failure of out of the plane. Yeah. So I increase the display factor. So out of the plane. This is pretty interesting. Yeah. Why out of the plane? Yeah, because we have here a failure of the weak axis of our HEB profiles. So the next eigenvalue is also out of the plane. Also interesting. And the next one is in the plane. Oh, okay. Okay. So when I would be a structural engineer, what I would do is avoid the bending, avoid the failure out of the plane by adding some lateral support. Okay. So let's take a closer look to the effective lengths. So when I would perform a stability design of steel members, I would take here this effective lengths, yeah, and this is 2, because here we have our Euler case 1. So the next one, this one, for example, here we have buckling length mode 3 of 1.5 around the strong axis. So when I would do a stability analysis of this steel column, the equivalent length or effective length would be here 9 meters. So maybe you can also take a other look to that one. Here, this is number 4. I take also a look to that one, number 4. And here we see, okay, the effective length factor is again on the, around the weak axis. In this case, 0.67. It's almost Euler case 3. So now I'm the structural designer, and I want to avoid the structural failure out of the plane. So what I do, add some lateral supports. So I will do this. I will add here these nodes on the top. Assign here nodal supports, but only activate the U-Y direction, because this will be my lateral support. I click on OK. I calculate the whole thing again. And one important thing is, don't mix the buckling shapes with the deformation shapes. Yeah, this is a huge difference. I show you why. So this is the global deformation depending on these vertical loads. And the stability analysis, so the buckling shape, is another one. So don't mix it up. So now we have the first eigenmode in the plane. Yeah, and this is maybe something what we know from the study. Yeah, it looks like that. And yeah, and now the critical load factor out of the plane would be here. This one, the second one, and I had to multiply here this 100 kilonewton with 100 again in order to get a stability failure out of the plane. Yeah, but this is quite unrealistic. But now you have a kind of feeling how the structure fails when they get too much compression forces. Okay, I think this was it. I have one last poll. Please give a feedback to that poll. Okay, perfect. I share the results, and yeah, perfect. Everybody has it right. Perfect. So the critical load factor is the factor by which the load can be increased before the system fails. Exactly. So, Ismail, are there any questions?
You've explained everything pretty well, Daniel. We don't have any questions so far. And
Okay.
If this is it, I would like to show our attendees a few things on our website.
Yeah, okay, of course. So
yeah,
you can take the control. You can assign you the rights as moderator.
mm-hmm.
Or I will give it to you. Just wait a moment. So now you can go forward.
Yeah. So there you go. Now you can see my screen, right?
Yes, I can see. I can see your screen.
Yeah. So yeah, first of all, thank you, Daniel, for the amazing presentation. We've gone through a lot of examples, even though we only had almost 3 hours. I just wanted to show you guys a few new things about our website. Since we have just released our RFEM 6, you can check it out on our website to see what new features we have in it. You can see here all the new features of RFEM 6 with videos available for every single feature. For example, if you see here under user interface, you want to explore a single feature a little more and see how, for example, RFEM shows you a photorealistic imaging of your model, you can check out the video here. I also want to say that as students, you might need a few things that we provide here for everyone on our website. We don't just provide solutions in terms of software. We actually provide you with useful informations in every specialty in civil engineering, concrete structures, masonry structures, every a little bit of everything, you know, all the application areas of our software. Here as students, this might be quite useful. The snow load, wind speed, and seismic load maps. This is one that you might want to use while you are solving your exercises. You can just enter the location of your building, the building you're calculating, and we will just, this map will provide you the value of the snow load according to the standards you're using. Another thing about our website that you might want to use, because it provides you with what you might not find the real definition for on Google. We have our own structural analysis wiki in which you find definitions, accurate definitions of a lot of terminologies. Let's say, for example, I want to look for member types, and I just type member, and you see, let's say, for example, eccentricity. You find you know, the definition of it. For another example, the member type, you find a more developed definition, since, you know, member type is quite a general term, and we are trying currently to make videos for every single term of these within the structural analysis wiki. One more thing, if you have any questions that we haven't answered during this online training, you can look for answers on our website using our FAQs. This is an example that I opened today, is you know, about the critical load factor that you talked about, Daniel, and similar definitions and solutions can be found on our website if you just type the words you're looking for in our FAQs. Another really useful feature on our website is the fact that you can download ready to use structure analysis models. You can download them from our website. You can see there's really a vast, you know, a really wide range of different types of models from which you can download. And by the way, this is really new. We started offering this like a month ago, I think, Daniel. We have opened the possibility for you guys to upload your own structural models. You can go to downloads and info and choose to submit your own structural analysis model. For example, I would say if you feel if you're feeling creative right now and right after this online training and you want to try RFEM and make your own model, and maybe you can submit it afterwards to our website, and we can post it on our social media as well. By the way, I really suggest you guys follow us on social media. We provide you with a variety of videos about pretty much everything. And speaking of everything, here's an overview of our YouTube channel where you guys can find our recent tutorials that we have uploaded a few months ago, where you can learn more and more about RFEM 6. And you know, if you go through our playlist, there's a lot of other useful videos that you can use to you know, make the process of learning RFEM really faster. And from experience, I'm talking to you guys, someone who started learning RFEM exactly a year ago, and it didn't take me as long as a few weeks to just, you know, really get a hold of all the functionalities that you can use in RFEM. So do not hesitate to download the free version for students. You can, if you submit your proof of immatriculation, you can of enrollment and in the university, you can get the full version of RFEM for at least 6 months. If you're going to still be a student, you will get a renewed license. So please, try to build your own models with RFEM. It's really not as complicated as you might think it is, because we have made our platform, our user interface, as intuitive as it can get. As you can see here, powerful, easy, and intuitive, which is the most important thing for me as a student when I was learning RFEM. So do not hesitate to try and build your own models using RFEM. If you are not a student, which is not the case for you, if you know someone who's not a student and would like to try that, you can download RFEM for free and get a license for 90 days, which is not a short period of time. In 3 months, you can do a lot with RFEM. So that would be it, guys. Just feel free to download and try to build your own models. Follow us on Facebook, LinkedIn especially. We post a lot on LinkedIn, Instagram. We're posting reels in the future, hopefully, and we will always be as active as you already probably know we are on social media. And with your help, we're always going to be this interactive. We try to organize events and trainings and webinars. And if you follow us and subscribe to our channels, you will always be the first to know whenever we have something like this organized.
Okay, perfect, Ismail. Yeah, Ismail put it on the point. So yeah, I would to thank you, all of you guys, by attending this webinar. I hope you liked it. I hope you learned something new, and I would really looking forward when I see you that the next time. Next week we have an introduction to the strength of materials with the program R section. This is also helpful for your study. And with these words, thank you very much. Stay healthy and goodbye.
Bye-bye.